So this is ELC 131, Circuit Analysis 1, and we're going to talk now about nodal voltages, or the voltages at a point in a circuit with respect to ground. Now, up to this point in our analysis of series circuits, we've talked solely about the voltage drop across resistors. And we've got a simple series circuit on the board. R1's 10 ohms, R2 20 ohms, and R3 30 ohms. And the calculations used to analyze this circuit are shown. We first calculate the total resistance. R1 plus R2 plus R3 is 60 ohms. We calculate the current in the circuit, Vs over RT, 200 milliamps, and then we find the individual voltage drops, VR1, VR2, and VR3, 2 volts, 4 volts, and 6 volts respectively. So in this circuit, current flows around. Again, we discuss or describe current as conventional current, and we'll have a voltage drop across R1 of 2 volts, a voltage drop across R2 of 4 volts, and a voltage drop across R3, 6 volts. Now, we talk about grounds in a circuit. There's 3 different schematic symbols, or 3 or more schematic symbols used to represent ground points in a circuit. And they are, on the far left, the symbol for an earth ground. This simply represents a point in the circuit that's connected to a copper or iron pipe that's driven into the earth. So this point in the circuit is at the same potential as the earth. We also have a schematic symbol used to represent a chassis ground. And this simply tells us that this point in the circuit is connected to the metal chassis of the piece of equipment. And we also have a schematic symbol to represent a signal common. This is just, again, a point in the circuit that's common with respect to some signal or some voltage. So with our series circuit, I'm going to connect this point to the earth. So this is my ground point, or the ground point of the circuit. And I'm going to describe some points in here, or nodes, that we can talk about with respect to the ground. Now, does this ground have anything to do with the current in the circuit? Well, let's look at an example. If you take the battery out of your car or truck and connect the positive terminal to a light, and take the negative terminal and connect it to a copper rod that we stick down into the ground, will the light be lighted? And the answer is no, because there's no reason for electrons to leave the earth and flow here. There's no difference in electrical potential between this terminal and the earth. In order for the light to be illuminated, we would have to connect the negative terminal to this same point. Current flows around through the light. The ground is nothing but just a point of reference. So putting the ground here has nothing to do with the current flow in the circuit. So let's calculate the voltage that will be seen at or be measured at node A with respect to ground. Now, in order to do that, all we're going to do is add up the voltages that exist from A to ground. So if we travel in this direction from A to ground, we have plus VR1 plus VR2 plus VR3. Going from A to ground, we have a drop in voltage, a drop in voltage, and a drop in voltage. So the voltage at node A with respect to ground will be 2 volts plus 4 volts plus 6 volts, or 12 volts. And I'll put a plus sign here. Now, I'm sure some of you are thinking, well, why did we go this direction to get to ground? Couldn't we have gone in this direction? And the answer is yes. I could have just as easily have said that the voltage at point A equals positive Vs, because from A to ground, I've got a positive to negative difference across Vs. So it doesn't matter how I get from A to ground, the voltage difference is the same. Now, to look at the voltage at node B with respect to ground, we follow the same procedure, and we simply add up the voltage differences from B to ground. So we find from B to ground a plus VR2 plus VR3 plus 4 volts plus 6 volts equaling 10 volts. Well, can I go from B to ground in this direction? And the answer is yes. The voltage at B with respect to ground traveling in the other direction would be minus VR1 plus Vs. Because going in this direction, I have a negative to positive drop across R1 and a positive to negative drop across Vs. Negative 2 volts plus 12 volts gives us, of course, 10 volts. So the voltage at node C with respect to ground is plus VR3. Well, I can also get from C to ground going in this direction. So I can also represent this as VC equals minus VR2 minus VR1 plus Vs minus 4 volts minus 2 volts plus 12 volts equals 6 volts. So you see, it doesn't matter which direction I go to get from A to ground, the voltage difference is always the same. And hopefully this makes sense, because if I go all the way around this closed loop, the sum of the potential differences always has to be 0. Now, could I put my ground right here and refer to this point as node C? And the answer is yes. I can put the ground wherever I want, because ground has nothing to do with current flow. Ground is merely a point in the circuit that's at the same potential as the Earth. Now, if I move the ground up to this point, the voltage at node A will be plus VR1 plus VR2. Because from A to ground, I have the difference across R1 and the difference across R2. I can go the other direction and say that VA equals plus VS minus VR3. Because if I travel in this direction, I have a positive to negative across VS and a negative to positive across R3. regardless of the path I take, the voltage from A to ground is 6 volts. Now, the voltage at node B with respect to ground is plus VR2, because from B to ground, I merely have this positive to negative drop across R2. Now I can go the other direction and say that the voltage at node B equals negative VR1 plus Vs minus VR3. Either way, I end up with positive 4 volts. Now the voltage at node C equals negative VR3, because from C to ground, the voltage is negative with respect to the ground point. Now, again, I can certainly go in the other direction. VC equals negative Vs plus VR1 plus VR2, which also gives us negative 6 volts. Doesn't matter how I get from C to ground, the voltage difference is always negative 6 volts. And this concept is sometimes confusing for students, but again, remember, we're just talking about the voltage at this point with respect to ground. And we do this all the time in electrical and electronic circuits so that we can provide a voltage at this point that's negative and a voltage at this point that's positive. Because quite often our amplifier circuits require both a positive voltage and a negative voltage.